Alright, gang, here we go. This is for Chem 2, Unit 13. We're talking about free energy and redox. We've kind of bounced around this idea for a couple of videos now, is the idea of, can we determine whether or not a voltaic cell will be spontaneous? If we mix these atoms, molecules, whatever they may be, together and set up our cell, will we generate an electric current? All right, and so we decided a while ago that if our Ecell is positive, we will have a positive cell potential, and then therefore will be spontaneous. Okay, and also know that this idea here is true whether it's a voltaic cell or just a general redox reaction. And so before we defined it as the cathode minus the anode, but really that's the same thing as reduction minus oxidation. So it doesn't really matter if we've set it up as a voltaic cell or if it's just some random redox reaction that's going on outside of a voltaic cell. Now, if we use this idea of our Ecell as defining our spontaneity, okay, we can also use this idea of Gibbs free energy, all right, to also define free energy. Okay, or Gibbs free energy is the idea of being able to figure out whether or not a process is spontaneous. All right, and so Gibbs free energy is essentially just a way of measuring how much extra energy do you have available, or do you have any. All right, and so remember that if your delta G is negative, then you have a spontaneous process. So if you have a positive EMF, that's spontaneous, and if you have a negative Gibbs free energy, then that is also spontaneous. So how do they relate to one another? It's this formula right here. Our delta G is equal to negative N times F times E. Now the negative N, that negative value just is what correlates the positive to the negative. The N value is the number of electrons that's transferred. All right, so the number of electrons that's transferred. F is the Faraday constant. It's 96,485 coulombs per mole. And then E is your cell energy. Okay, and so you can also do this under standard conditions. And if you do that, then this would simply become delta G naught, or a standard, and then Faraday's constant and the number of electrons won't change, but this guy would become standard conditions. And so we can relate this to either standard or non-standard conditions. All right, and so remember our original formula to find delta G was this, negative RT natural log of our K value. Okay, and so we can use delta G and this new idea of this for redox reactions to relate the cell potential, Gibbs free energy, and the K value for whatever our reaction is, our equilibrium constant. So this little triangle gives us an idea of how we can convert between the three different ideas. So if you're given delta G, you can use this formula to convert to E, or this formula to convert to K. Right, and then if you have K, you can go back to G, or you can go over here using this amalgamation of the two of these without actually knowing your delta G at all, which is kind of handy. And then being able to go from E, you can go, either way across that triangle. All right, so let's do a practice problem here. It says use the standard reduction potentials to calculate the standard free energy change and the equilibrium constant for this reaction. So we got silver plus oxygen, hydrogen yields silver and water. So this is a redox reaction. And then part B says suppose the reaction in part A is written as this. What are the new values of E, delta G, and K? All right. So yeah, so this isn't too bad. What we need to find, so for A, we're just going to find each of those 3 points on our graph here. So for A, what we got to do is we're going to use our values, our reduction potentials here, figure out which one's oxidized, which one's reduced, and then follow our formula. Then we can plug them in to our two formulas and then find out what our values are. So that's not too bad. Okay. So we'll break that thing down into its two half reactions, which is exactly what we do here. The oxidation is balanced to give you 4 and 4, and these are your reduction values right there. So we can say cathode minus anode, all right, reduction minus oxidation. So you take 1.23 minus the 0.80 right here. So your overall reduction, or your overall cell potential is 0.43 volts. Okay, we can take that value, right, and plug that into our new equation we just learned for Gibbs free energy. Delta G equals negative NFE. The 0.43 is our E. F is Faraday's constant, the 96,485. And then the negative N value, remember the N is the number of electrons, and there are 4 electrons being transferred in this guy, so there would be 4. Multiply that all out, and we get this guy Gibbs free energy is always in kilojoules. Watch out for that because it's usually a fairly big number. So negative 170 kilojoules per mole, and since we had a positive cell potential, we should have a negative delta G, so that's all good. Now we can just take that, plug it into our RT natural log of K to find our K value. Pretty simple enough, so you can plug this guy in here, solve him for natural log of K, right? So divide this guy over, and then you can say, to get rid of the natural log, so you say e to the 69th power. And so you get 9 times 10 to the 29th. Notice that's a really absurdly big number, and that makes sense because delta G was a really large negative number, so this should imply that our products are favored. All right, now it says, well, let's take the whole thing and divide all of our coefficients by half. So we only allow half of as much of it to react, and it wants us to know the new values. Well, the values of the reduction potentials, remember these guys here, these are an intensive property, right? This is intensive, so it doesn't matter how many of them react, you're always going to have the same reduction potential. It's completely independent of how much you have. And so your Ecell doesn't change. However, in your formula, delta G equals negative NFE, that N value, remember, is the number of electrons you have, and in this case, since you're reacting half as much, your N value is 2, so your delta G is half as much as it should be. Right, so there's that, and then we can take that to plug it into our new value for our K, solve for it exactly the same. Notice that it's not exactly half anymore, right? It's 4 times 10 to the 14th, very different number. So our K value doesn't go down by exactly half, but the delta G did. All right, let's see if we can do one. All right, it says for this reaction, big and sucker. All right, it says delta G. Standard is 87 kilojoules per mole, given the standard reduction potentials of nickel and table, and I pulled that out earlier. That's the negative 0.28. What value do you calculate for the standard reduction potential of this chromate thing right here? All right, cool. So if we're trying to find the standard reduction potential for just this guy, this one's being reduced, right? So we know that our Ecell is equal to E reduction of the cathode minus E reduction of the anode. Okay, well, we have this value right here, right? This value is the negative 0.28. This is what we're trying to find, the reduction at the cathode, because that's what the chromate is. So really we need to be able to find the Ecell. All right, so if we can find the Ecell, then we can rearrange this. So just our reduction of the cathode would simply be the Ecell plus the 0.28. All right, so we could rearrange that just to save us some time later on. So the E reduction of the cathode would be equal to the Ecell plus 0.28. All right. So let's see what we get here. All right, let's see. So we really just need to find the Ecell. Well, we know that delta G standard is equal to negative NFE standard. All right, so that means E standard is equal to delta G standard divided by negative N times Faraday's constant. All right, now notice we got to watch out for something here. Delta G is in kilojoules per mole, but our E value is in volts, which is just in joules. So we got to convert this to this. So this would be 87,000 to 3 joules per mole. All right, so we take 87,000 divided by our negative N, and our negative N here is the number of electrons, which is 3. All right, so 3 times our Faraday's constant, which is 96485. All right, so we take 87,000 divided by negative 3 times 96485, and I got negative 0.301. Negative 0.301 volts. So all we have to do now is plug this guy in. So negative 0.301 plus 0.28. So the E reduction of the cathode is equal to plus 0.28. I got negative 0.02. -0.02, which is the correct number of sig figs because we added these guys together. Remember, when you add them up, you line them up, and you can't go any farther, so we have to stop at the hundredths place, which is this guy, so -0.02. All right, so it'd be that guy right there. All right. All right. Non-standard conditions actually give us an interesting conundrum here. So you remember, so your Gibbs free energy, delta G naught plus RT natural log of Q. So that's what we just established. That we established this before. All right, and we know delta G equals negative NFE. All right, and so we can plug this guy in here. So this would become this. All of this would become this. All right, and if we divide both sides by this, all right, then they cancel and we start reducing this thing, so we get this guy right here. And this is known as the Nernst equation. All right, it's a way of being able to find your cell potential given your standard and then whatever your current conditions are. Okay, and then if we go ahead and take our RT and F values, plug these guys in, if we're at standard thermodynamic temperature constants, we get this. And so this is the Nernst equation that we're going to focus on here. This E equals E standard minus 0.0592 N over log of Q. Now remember, Q is your reaction quotient, and you calculate Q the same way you calculate K. It's just under the current conditions that you're at. All right, so let's walk through a practice problem here. So you want to calculate the EMF at 298, so that's our standard temperature, which is nice, generated by a voltaic cell in which the reaction is this: dichromate, hydrogen, iodine, blah, 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 and we've got new concentrations. So we're no longer at standard EMF because we don't have 1 molar of all of these things. Some of them, like dichromate is twice what it should be, and the chromate ion is way less than it should be. All right, so what we need to do is we're just going to plug everything into that formula we just learned. So the first thing they're going to solve for is their Q value. All right, so they find their Q value. Remember, so Q would be equal to this right here. Remember, for your equilibrium constant, you don't you put products over reactants. You don't include anything that is a solid or a liquid. Okay, and remember, you raise things to their coefficients, so the chromate becomes squared because it's 2 right here. The dichromate is to the 1 power because it's just one of them. Hydrogen goes to the 14th power, and iodine goes to the 6th power. Okay, and we've got these new concentrations they give them right here, so we can just take those guys, plug it in, and so we get a Q value of 5 times 10 to the minus 5th. Or 11th. What? 5 times 10 to the minus 11th. Now we also need our standard potential, and we calculated that in exercise 20.6. So we're just going to run with it. But if you didn't have it, it'd be easy enough to do with that standard reduction potential. You would just take your iodine and your chromate and go cathode minus anode and all that. And then we also know our N value is equal 6. All right, and if you didn't have that, really what you'd have to do, the first step, is to split this guy into your 2 half reactions, so you could see how many electrons are transferred and then balance those guys. So we're saving ourselves some time here. All right, so then all we have to do is take those values, plug them into our equation, 0.79 minus our 0.0592 over our N value of 6, and that's the log of 5 times 10 to the minus 11th, blah, 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 and you get this. Okay, so, yep. All right, and this is what we expect because that means our dichromate is more. Our dichromate was at twice the concentration of what it is standard, right? And since the reactant was higher than that, it makes sense that we'd produce more voltage. All right, it says consider. Now let's do this one together. See if we can do it blind. You ready? It says consider a voltaic cell whose overall reaction is lead plus zinc goes to lead plus zinc ion. What is the EMF generated by this voltaic cell when the ion concentrations are those? All right, so split this up into our 2 half reactions. Pb2 plus 2 electrons would go to Pb solid. And I'm not, I can easily tell there's no hydrogen or oxygen in here, so this makes balancing these half reactions pretty dang simple. Zinc 2 plus, and this would be aqueous, but whatever, aqueous plus 2 electrons, and this would also be aqueous. All right, so our E would be equal to our E standard minus R, or 0.0592 over N times our log of our Q. Okay, so our E value here, we need to calculate our E. So our E, the reduction of this guy, our standard reduction, is equal to, so our lead, I've got it pulled over on my other screen. Where'd you go, sucker? lead was negative 0.13. All right, and then the reduction of the zinc, negative 0.76. So, so we do cathode minus anode, so a reduction minus oxidation, and so the lead is being reduced, so it would be negative 0.13 minus a negative 0.76. All right, so you get positive 0.63, so 0.63 minus 0.0592 divided by our n value. The n is how many electrons are transferred, which is 2, which is a good thing we balanced those half reactions, so that's 2, and then the log of our Q value. Okay, so the Q value is, we're going to look at this equation here, not the half reactions. We got to look at the overall reactions. Remember, it's products over reactants, and we don't include solids, so that means we wouldn't include our solids, these guys here. So essentially, it just turns into the concentration of zinc over the concentration of lead. All right, concentration of zinc was 0.55. Concentration of the lead is 1.5 times 10 to the minus third. All right, and we should be able to just plug all that in and see what we get. 0.0592 divided by 2 times the log 0.55 divided by 1.5 e to the minus third. Oops, got to actually press the button. All right, and I got 0.56 volts. There you go, 0.56 volts. All right. Cool. So anyway, so that's Nernst equation. It's not too bad. It's just a little bit more of the same. Just, you know, hopefully you're getting the swing of how chemistry works. You just kind of, or at least how you know, general chemistry works until you start to get to organic chemistry, which is a whole different beast. But and then physical chemistry is a whole different beast from that. So isn't that fun? But anyway, so hopefully you're starting to feel like, you know, I just have to take it a little bit at a time. So do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.